Howdy everyone, it's Joe, and recently I had a problem. I was working on a personal project of mine, a TUI recreation of the 2009 game Lose Lose. It was a game like Galaga, except when you destroy an enemy spaceship, it will delete a completely random file on your machine. I thought it'd be fun to find a way to force someone to play this game on their terminal. To do this, I moved to learning about process injection, and I found this difficult, and I wanted to bridge the gap in knowledge for newcomers like me. Before continuing, I want to mention I have a write-up of this topic on my site loser404.dev if you prefer reading. Additionally, as a quick disclaimer, I'm not encouraging anyone to use this information to cause harm of any kind. First, let's establish a goal. What we're trying to accomplish is an effective hijack of another user's process. We'll then use this hijack to run our own code. To accomplish this hijack, we'll inject shellcode into the target process's memory through the ptrace syscall. If you don't know what ptrace is, then don't worry, we'll go over it. Secondarily, we'll need to go over the very basics of how to write shellcode. Just to clarify, this tactic works on Linux and not Windows. You'll have to use something like DLL injection to accomplish that. Additionally, when writing the shellcode, we'll be writing it in x86-64. If you'd like to best understand this video, I suggest you are familiar with the following: x86-64 assembly, Linux system calls, and the general concepts of process memory. First, let's cover what ptrace is. Simply, it's a syscall that allows our process called the tracer to modify the execution of another process called the tracee. We'll use this to execute our shellcode. The ptrace syscall takes 4 arguments: operation, PID, address, and data. The operation and PID arguments always have to be specified, but the address and data do not. However, it should be noted most programming languages include libraries that have functions for each ptrace operation. Now let's go in depth into how ptrace injection is going to work. First, the process that we own will send a ptrace syscall to our target with the operation ptrace attach. This will set up our tracer-tracee relationship and send a sigstop syscall to the tracee. This will stop its execution. With sigstop being sent to the tracee, our process will wait for the tracee to stop execution. Next, our process will send the ptrace operation ptrace syscall to the tracee. This will tell the tracee to resume, but stop again after the next instruction, or the entry to or exit from the next syscall. Once again, our tracer process is going to wait for the tracee to stop execution. With execution stopped, our tracer process can now use the operation ptraceGetRegs to retrieve the register values from the tracee process. We can now write our shellcode to the tracee process. We'll do this with the ptracePokeData operation, and we'll use the instruction pointer that we retrieved as the address we're writing to, and our shellcode as the data we're writing. This will write our shellcode as the next instructions to execute within the tracee process. Finally, our process will tell the target process to resume with the ptraceCont operation. Optionally, you can also use the ptraceDetach operation to terminate the tracer-tracee relationship, but that's not needed for the injection to work. With all these steps completed, the target process is now running our shellcode, giving us control. Alright, now that we know how ptrace injection works, let's review how to write shellcode. First off, there are tools such as the MSF Venom that allow you to write shellcode very easily. There are also sites like ExploitDB that show people who have posted their own shellcode for people to use. However, I think that you should know how to write shellcode on your own before using those so that you best understand it. Additionally, in this example, we're going to be using NASM as our assembler, so if you're following along, please make sure you have that installed, and we'll also be making plenty of use of syscalls. I'll link a reference in the description for you to reference all of those. Alright, first let's go ahead and start with an assembly program that just executes bin bash. This would be something that we might want to use in our shellcode, for example. Let's go ahead and assemble it with NASM, TAC-ELF 64. We're going to output it to the same name but with an object file, and we're going to use our ASM file. Then we're going to go ahead and link it, again, specifying the output. And we see we now have the executable. Running this, we see that we're running bash. Now let's exit out of this. Let's go ahead and view what the hex might look like for this program. We can use objdump, tecd, and specify our object file. And now we can see the hex for our executable. Unfortunately, we can't go ahead and use this code just yet. We need to make some changes. You might notice that there are a few problems with this. First and most notably, our bin bash string does not appear anywhere in here. We need to find a way to put it within the text section of our code. The easiest way to do this is with a jump call pop sequence. We'll go into that in a bit. Other problems that we have is there are lots of null bytes. Not only does this add a lot of unneeded space, a lot of functions, like in C for example, will use null terminators to denote the end of a string. We don't want anything being misconstrued as that, so we need to find a way to remove them. Additionally, one final thing that we could add is a 2-byte NOP sled, which is just 2 sequential NOP instructions, which are important because if we get interrupted by a syscall, it might try to jump two bytes back. So we want to make sure that if that happens, our NOP catches it and is able to push us forward. So now let's go ahead and get to fixing these issues. First off, let's tackle the jump call pop sequence. To do this, our aim is to put this string onto the stack. Starting out, we're going to go ahead and create 3 separate sections: our start, our payload, and our string section. Our start section is going to start out by jumping over to the myString section so that it goes over all of this code. Our myString section is going to call the payload section, and below this, we're going to go ahead and put our string reference. And then finally, rather than moving this value into RDI, we're going to go ahead and just pop off the stack into RDI. We're also going to move this one up. And now we can go ahead and remove this data section up here. What this has effectively done is we start out our code by jumping down and going over all of our other code to the myString section. The myString section says, jump over to payload, but before you do that, put the address to the next instruction onto the stack. This is so you could return to it, but we're going to use it for our own advantage. And when we jump over to payload, we're going to say, take the address off the stack and put it into the value RDI, which is needed for the exec syscall. Now we can go ahead and run our code again and see that it still executes, which is great. And we can check again to make sure that we can now see what is our string appearing within these sections, which is great. But this did bring up one additional issue. Adding that string added some null bytes. So let's go ahead and tackle taking care of those null bytes. First off, null bytes are caused by the zero fill that is caused by 64-bit registers being used in x86-64. So what we need to do is we need to find a way to either fill these registers or not reference the entire 64-bit values when using this. For our string, this is quite simple. We can go ahead and just add some backslashes, and that will go ahead and get rid of these null bytes because we've added 2 more characters. However, for our other values, we can go ahead and just use a push pop sequence. So rather than moving the value 59 into the register RAX, we're going to go ahead, push 59 onto the stack, and we're going to pop it into RAX. That solves this issue. Unfortunately, we cannot push 0 onto the stack because that's going to push a null byte. Instead, we can use a different method. We can XOR the register with itself. So if we XOR RSI with RSI, that's just going to create 0. Same thing with RDX. You might have noticed we haven't done this for the exit syscall. That's because we don't actually intend on exiting it gracefully, so we can actually take advantage of this and outright remove this string. It is not needed. Our program won't exit gracefully, but we don't actually need it. Additionally, let's add that 2-byte NOP sled that we were talking about. If you don't know, NOP just stands for no operation. That way if we get interrupted here and it tells us to jump 2 instructions back, what we're just going to do is hit this NOP sled and it's going to no operation, and continue along. So now we have modified our code and it should satisfy all the conditions we're aiming. Let's go ahead and compile it to make sure it works again. Still running bash, that's great. Let's go ahead and check the obj dump. Now let's look for any errors that we might have. We see no null bytes, no null bytes, no null bytes. Our string is contained within this code, and we have our NOP sled. So we have satisfied all the conditions that we're aiming for. Now that we know that our hex is valid, let's go about and make a shellcode file, which just goes ahead and takes all that hex and puts it into a nice file for us, so that we can go ahead and use that to inject into our process. So to do that, let's go ahead and use our object file with obj copy this time. J, we want the text section, we want binary, we're going to go ahead and use start.o, reference our file there, and we're just going to call this a shellcode file. And now if we use xxd, we can go ahead and see all that is now in hex. Yes, there's going to be some null bytes here. In this case, these are fine. Now let's go ahead and verify that our code can actually work within an injection context. And for that, I'm going to use this GitHub example that I'm going to link in the description. Let's go ahead and git clone this Linux injector. Go into here. We can just run make. Next, let's go ahead and create a process for us to inject into. New window. Let's find the process of this. It is 4154. Injector 4154, and this one just takes the file outright, so we can go ahead and use our shellcode file. We also have to use sudo for this. And we see the injection was successful. I'm now running bash here. It's having some issues with standard in, but we can see it still does execute code. And this is great. This demonstrates that our process has actually injected successfully. And because our process has injected successfully, we know that our shellcode is valid, and we can go ahead and use it in our ptrace example. Having covered how the injection works and how to write shellcode, you now have everything that you need to know. But first, let's go over some things from a blue team perspective. There actually are some protections within the Linux kernel via YAMA. This is called ptrace scope, and you can find it in the path/proc/sys/kernel/yama/ptrace scope. The value in here is going to be on one from 0 to 3. This is going to control what processes are allowed to attach to others. By default, on most distributions, it's going to be 1, but you can change it from 0 to be the least protective to 3 to be the most protective. Additionally, ptrace does have plenty of legitimate use. It's very often used in debuggers to modify the execution of child processes. So just seeing it alone does not mean that someone is using an injection on your host. And that's all I have. I just want to say I made this because I was having trouble finding a good resource when I was trying to learn this myself. And I do want to point out that there are plenty of other tactics other than ptrace that you can use to inject into a process. Additionally, there are limitations with this approach. As stated before, there are possible issues that you can have with YAMA, but our setup requires you to have sudo privileges, which if an attacker has, it's already game over. You don't really need to inject into processes. You can just kick everyone else out. However, I found this a really fun project to work on, and I hope you all enjoyed learning about it with me. Hopefully, you're able to take something away from this and create something cool. Thank you.